Let's now turn to borehole seismics. Borehole seismic surveys, also known as vertical seismic profiles, or VSPs, are acquired with the source on the surface and receivers at known depths in the borehole. The key difference between borehole seismics and surface seismics, like towed streamer, OBS, land surface, or even the vertical cable, which we will discuss later, is that surface seismics covers a large area on the order of a couple of hundred square kilometers, whereas borehole or well seismics cover just the vicinity of the borehole, but with higher resolution. High resolution here means that we can see more geological details from borehole seismics than from surface seismics. In other words, we can easily identify the structure in the order of 5 meters or smaller in borehole seismics, but rarely in surface seismics. One of the common functions of borehole seismics is to help find the precise location of the well in the 3D image of the subsurface, derived from surface seismic data. Let's repeat this. One of the most common functions of borehole seismics is to help find the precise location of the well in the 3D image of the subsurface, derived from surface seismic data. In other words, now that we have identified from surface seismics our zone of interest, that is, oil reservoir, for example, it is time to increase our understanding of the zone of interest with borehole seismics. We now describe the typical borehole seismic acquisition geometries and corresponding data. The simplest borehole survey is the Checkshot, or velocity survey, in which receivers are stationed at specific intervals, often separated by hundreds of meters, in the borehole, while the surface source is fired nearly vertically above. The receiver records the travel time from source to depth at several depths, and a table of the seismic velocities between the depth stations is constructed. Here is an illustration of a Checkshot survey. We have a sensor inside the borehole and a shot point near the borehole. We use the time-depth ratio to estimate the velocity model. Let's now discuss our second borehole acquisition geometry, that is, zero offset VSP. Here we mean that the shooting point is very close to the borehole, by less than 100 meters or so. The receiver and source configuration in zero offset VSP surveys is similar to that of Checkshot surveys. The key difference is that in zero offset VSP, we are interested in measuring the full waveform instead of travel time only. So the goal is to obtain an image of subsurface reflectors from the waveform. A higher density of receiver positions is used in zero offset VSPs compared to Checkshot surveys. And trace recordings extend beyond the first breaks, that is, the first arrivals at the receivers, to include later times at which the reflections arrive. Here is an illustration of zero offset VSP. The source is located directly above the receivers. In marine experiments, the source will most often be an air gun, whereas on land, they will be either dynamite or a vibrisized source. The physical quantities recorded in this experiment can be the borehole fluid pressure. We can obtain this pressure by suspending hydrophones in the borehole. Hydrophones are sensitive to fluid pressure changes as the seismic wave passes in any direction. We can also record the particle velocity vector in zero offset VSP by clamping geophones to the rock formation. Remember that geophones sense the motion of the rock formation and can record the 3 components of the particle velocity. There are basically 2 types of events, those that are downgoing with respect to the receiver position and those that are upgoing. All reflected events below the receiver location are upgoing. The classical objective of seismic imaging of VSP data is to image upgoing energy. Notice that the downgoing wave field contains all direct waves and some multiples. So the processing of VSP essentially includes the separation of downgoing waveforms and upgoing waveforms, multiple attenuation, and the imaging of upgoing primaries. The apparent time difference across the receiver array between the downgoing and upgoing waves is generally exploited for up-down separation. We will provide examples in future lectures. The 4C recordings, that is, hydrophones and 3-component geophones, can also be used for up-down separation. Again, we will provide examples in future lectures. Notice that the reservoir, or the zone of interest, is generally located below the sensor in the borehole. That is why we image the upgoing data instead of the downgoing data. Let's now discuss our third borehole acquisition geometry, that is, Offset VSP. Here we mean that the shooting point is a kilometer or more away from the borehole. Let's repeat this. We're now discussing our third borehole acquisition geometry, that is, Offset VSP, which in this case means that the shooting point is a kilometer or more away from the borehole. In the Offset VSP, a single surface source is positioned at a substantial distance from the well, as illustrated here. This distance is called an offset. The substantial offset from the source to the well is designed to shift the reflection points away from the well, so that the subsurface coverage can be extended away from the well, and thus the Offset VSP can help to detect heterogeneities away from the well, or the borehole. Let's now discuss our fourth borehole acquisition geometry, that is, Walkaway VSP. The Checkshot, Zero Offset VSP, and Offset VSP techniques described above are multi-receiver, single-source techniques. The Walkaway VSP departs from these configurations. In its simplest form, a receiver array of 5 to 7 geophones collect data from multiple surface source locations along a line that extends from the well. Again, Walkaway VSP is a multiple source survey, while the previous 3 borehole surveys are single source surveys. That is the key difference. Each line typically has hundreds of source positions. Reflections from each horizon below the geophone offer an umbrella-shaped coverage of the formation, alongside and beneath the well. These data may then be processed to create an image that usually has a higher resolution than that available from surface seismic surveys. The acquisition of VSP with multi-line Walkaway profiles, or 3D profiles, will be discussed later. This figure shows 3 examples of Walkaway VSP shot gathers, corresponding to the model in the previous slide. To facilitate the inspection of the different events contained in Walkaway VSP shot gathers, we have used 30 receivers. This is quite a large number compared to the number in standard Walkaway VSP experiments, which generally have only 7 receivers. Notice that contrary to zero offset VSP data, it is quite easy to detect the effect of large heterogeneities away from the well in Walkaway VSP data, especially when data are organized in receiver gathers. Note also that data in Walkaway VSP shot gathers resembles those of the zero offset VSP, in the sense that we can quite easily differentiate between downgoing and upgoing events. We have marked here in red some of the downgoing events. However, as the shot moves substantially away from the borehole, we can notice that the quasi-parallelism between downgoing events and zero offset data is no longer valid due to heterogeneities away from the well and toward the offset. A similar observation can be made for upgoing events. This figure shows 2 Walkaway VSP receiver gathers for the same model as in the previous slide. We can remark that receiver gathers look like standard surface seismic data. Again, notice that contrary to zero offset VSP data, it is quite easy to detect the effect of large heterogeneities away from the well in Walkaway VSP data, when data are organized in receiver gathers. Note also that when Walkaway VSP data are organized in receiver gathers, it is quite difficult to differentiate between downgoing and upgoing events. The red arrows here indicate some of the reflections caused by lateral heterogeneities. Let's now discuss our fifth borehole acquisition geometry, that is, Walk Above DSP. Somewhere between the single source and Walkaway VSP is the VSP in deviated and horizontal wells, often called a Walk Above DSP. In this technique, sources may be positioned directly over the receivers to map a deeper reflector than the deviated borehole. The Walk Above VSP are also used to simply locate the positions of the deviated well onto surface seismic sections. One use of Walk Above VSPs today is to help locate lateral anomalies of elastic parameters, which are not clearly visible in images obtained from surface seismic data. Another use of a Walk Above VSP is to improve seismic resolution below the deviated portion of a well. As with any VSP survey, there is usually a desire to perform an up-down separation. Unlike vertical wells, and just like surface seismic data, there is no apparent time difference across the array between the downgoing and the reflected upgoing waves. In this case, the strategy for dual field recording using hydrophones and geophones is essential for up-down separation. Let's now discuss our sixth borehole acquisition geometry, that is, salt proximity VSP. Salt proximity surveys are recorded in wells adjacent to salt domes, with the source placed immediately above the salt domes. Travel time information and the polarization of first arrivals are measured by the downhole geophone at various locations in the well. When the location of the receivers and the source are known, and when the velocity of the salt, the velocity of the sediment layers, and the distance to the top of the salt dome are also known, then travel times can be used to determine the locations of points where rays exit the salt dome. These locations allow us to construct a profile of the salt dome, which may be used to determine the lateral distance from the well to the salt, and also to identify possible overhangs and potential traps along the salt flank. Note that it is important to position the borehole quite close to the salt flanks to reduce the interference between the first arrivals, which are also known as first break, and the latter arrivals. Here are two shot gathers of salt proximity experiments. One is located about 100 meters from point A of the flank, and the other about 450 meters. We can see that the first breaks are much more clearly defined in the case in which receivers are closest to the borehole. Let's now discuss our seventh borehole acquisition geometry, that is, Shear Wave VSP. As the name suggests, we can see here Shear Wave VSPs are recorded with shear wave sources, usually shear wave vibrators like the emerging marine seismic vibrator. Shear Wave VSPs may be used in a manner similar to P-Wave VSPs to create a high-resolution image of reflectors. However, another application is to measure a phenomenon known as shear wave splitting, which is associated with anisotropy caused by stress or vertically aligned fracture systems. Shear waves travel faster when their particle motion is polarized in the plane of the fractures than when it is perpendicular to the fracture plane. Thus, shear wave VSPs can be used to determine the expected orientation of induced fractures, the orientation of natural fractures, and stress directions. They can also be used as a qualitative indication of fracture density. Let's now discuss our eighth and last borehole acquisition geometry, that is, Drill Noise VSP. The drill bit seismic technique, sometimes called Drill Noise VSP or seismic while drilling, reverses the geometry of the source and receiver. The drill bit itself is the seismic source, and receivers are placed on the surface. The processing of the drill bit data can help us to image the reservoir or a drilling hazard, such as overpressure, as the well is being drilled. Ordinary VSPs can indicate such features below the current total depth of the well by flagging zones of anomalous acoustic impedance. But VSP data can be converted to depths only as far down as the lowest borehole receiver level. After that, results are in time, and so they are not very useful to drillers. The drill bit seismic technique can complement the time-based acoustic impedance profile derived from VSPs by providing a means to measure the time depth information below the bottom VSP receiver level as the drilling progresses. Thus, the depth index of the acoustic impedance prediction can be continuously updated at the well site, showing clearly when a suspected drilling hazard is about to be hit. However, this information is not easily available because the vertical axis of the seismic section is measured not in distance, but in two-way time, the time seismic waves take to travel through the earth, bounce off a subsurface reflector, and return to the surface. To relate the position of the bit to the seismic section, it is necessary to convert the vertical axis from time to depth. This conversion requires knowledge of the velocity of seismic waves through the formation. Velocity varies significantly with rock type and usually has to be measured rather than modeled using a combination of sonic logs and borehole seismics of a well after it has been drilled. Let's now revisit Walkaway VSP to describe its 3D versions. VSP imaging surveys, such as Walkaway's, have been used for a number of years to image structural complexity away from the borehole. These Walkaway profiles are essentially along one direction. For this reason, these profiles are generally characterized as two-dimensional or 2D. Moreover, the imaging of these profiles is generally confined to the vertical plane containing the line of sources and the borehole. Because of the proximity of the receivers to the target, like all VSPs, these 2D images usually have the advantage of being of higher resolution than their surface seismic counterparts. But, by definition, 2D walkaways do not describe the full volume of the reservoir. Fortunately, the acquisition principle may be extended to cover 3D media by repeated profiling in parallel lines, in effect, by collecting a series of 2D Walkaway surveys, similar to those collected in marine towed streamer seismic data acquisition. Three-dimensional VSPs, as depicted here, allow high-resolution imaging to augment surface 3D surveys and make it possible to obtain images beneath surface obstacles, such as platforms, and near-surface obstructions, such as shallow gas zones. In addition, because the acquisition conditions and processing steps of VSP surveys are accurately reproducible, 3D VSPs open up the possibility of time-lapse or 4D seismic surveying. Here is a distribution of shot points in a 3D Walkaway VSP survey over the Ecofist oil field. Note that shot points are colored blue, with some sparse green and red points. Red points correspond to cases of gun failure, and green points correspond to shots outside the original survey plan. This distribution is typical. Here are results of 3D imaging. The left figure shows the imaging results of the 3D Walkaway VSP data obtained from this survey described in the previous slide. These results are overlain on towed streamer data to show how the 3D Walkaway VSP can improve the resolution of towed streamer data, especially when the resolution of towed streamer imaging may be poor due to shallow gas zones, for instance, as it is in this case. The key obstacle to the development of 3D VSP is rig time, as production or other measurements must stop while conducting 3D VSP experiments. Today, a 3D VSP of 41 lines of 200 shots takes about 40 hours. It is difficult to convince an oil producer or driller to shut down production or to stop drilling for that length of time. In summary, the key obstacle to development of 3D VSP is rig time, as production or other measurements must stop while conducting 3D VSP experiments. Today, a 3D VSP of 41 lines of 200 shots takes about 40 hours. It is difficult to convince an oil producer or driller to shut down production or to stop drilling for that length of time. The benefits of VSPs are higher resolution than TWS, OBS, VC, and more at the vicinity of the borehole. Actually, one of the functions of the borehole seismics today is to help locate the precise location of the well in the 3D image. Now let's talk about tube waves, which are associated with all of the borehole experiments described above. These are unwanted waves, but unfortunately part of the borehole acquisition process. Waves traveling in a fluid-filled borehole or on the walls of a borehole in the direction of the axis are called hydraulic waves or tube waves. Tube waves being localized to the borehole radiate very little energy into the formation, at least for some medium parameter ranges. This observation implies that tube waves will have high amplitudes. They are therefore considered a major source of noise in VSP data. The most important wave mode localized to the borehole is the interface Stoney wave. This wave mode is slightly dispersive, but for seismic frequencies, the low-frequency approximation applies. Its velocity is always smaller than the velocity of the drilling fluid. Here shows the hydrophone recording in a zero-offset VSP experiment that was run in offshore Norway in 2001. The dominant strong amplitude mode on the hydrophone section is the tube wave propagating in the fluid column of the borehole. In the upper part of the section, which has casing, the tube wave velocity is almost constant. The tube wave reflection at depth 1,300 meters is caused by the casing of about 13 inches thickness. The varying and quite long signature is most likely related to the coupling between the casing and the formation. Below the casing shoe, the hole is open so that there is coupling between the drilling fluid and the formation. As the tube wave or Stoney wave passes, the drilling fluid interacts with the pore system of the formation, resulting in attenuation and loss of high frequencies of the tube wave as it propagates down the open hole. Now let's take a small quiz. Why don't most of the VSP experiments include sources like air guns or dynamite in the boreholes with receivers at the surface? Here's your answer. These sources can destroy the borehole and therefore stop oil production for months. Let's now conclude these lectures on seismic acquisition geometries and seismic data by talking about vertical cable acquisition. Marine vertical cable acquisition is performed with a number of vertical hydrophone arrays deployed in the water column as illustrated here. In areas congested by platforms or other obstacles, vertical cable or VC seismics is emerging as an alternative technology to surface seismics, because it operates with small boats without the cumbersome towed streamers. Another advantage of VC technology is higher quality data, because the receivers are in a quiet environment compared to the near-surface environment, which can be affected by ocean swell, under which measurements like towed streamer data are made. This idea of VC cable acquisition had its genesis in Walkaway BSP, with the important differences that it constitutes a VSP without borehole tube waves or expensive standby rig time. It was first proposed by Krell in 1994. Again, this idea of VC cable acquisition had its genesis in Walkaway VSP, with the important difference that it constitutes a VSP without borehole tube waves or expensive standby rig time. It was first proposed by Krell in 1994. Moreover, VC acquisition is aimed at imaging a large area just as towed streamer and OBS acquisition do, not just the vicinity of the cable as VSP. Although the basic idea behind VC acquisition is quite simple, its implementation is not, as it requires an ocean engineering effort of a completely different type from marine towed streamer acquisitions. For example, the hydrostatic pressure at a depth of 600 meters is 860 psi, compared to 28 psi at the normal operating depth of 10 meters for a streamer. So a cable of a receiver specially designed for deep ocean depths is required, as well as special high-pressure calibrated hydrophones. Another major challenge is keeping the cable vertical, as ocean currents can cause a significant tilt on the cable. Mechanically, the cable is kept vertical by anchoring it at the sea bottom and by the buoyants at the sea surface. Most current VC data processing schemes can tolerate up to a 5-degree tilt. Notice that VC acquisition is actually designed for deep water E&P. The experiment suggests that for this technology to be effective, the water depth must be about 500 meters or more. Let's look at some marine VC data, starting with the typical events. Here are examples of primaries, receiver ghosts, and free surface multiples in VC data. One of the major differences between VC data and surface seismic data, in particular towed streamer data, is the nature and use of receiver ghosts. In surface seismic data, the effect of receiver ghosts is negligible. They are generally treated as part of an effective source signature because the receivers are very close to the sea surface. In VC experiments, the problem is quite different. The receiver ghosts can be distinct from primaries and multiples, as illustrated here. These figures show an example of a VC shot gather and receiver gathers of synthetic data. As expected, the shot gathers on your left look just like standard VSP data, and the receiver gather on your right looks like standard surface seismics. We can see that most of the events are linear, with opposite gradients. Just as in VSP data, downgoing events have positive gradients, whereas upgoing wave-filled events have negative gradients. This difference in the sign of the gradient between upgoing and downgoing waves can be used for up-down separation, as we will see in later lectures. Again, one of the major differences between VC data and surface seismic data, in particular towed streamer data, is the nature and use of receiver ghosts. In surface seismic data, the effect of receiver ghosts is negligible. They are generally treated as part of an effective source signature because the receivers are very close to the sea surface. In VC experiments, the problem is quite different. The receiver ghosts can be distinct from primaries and multiples, as illustrated here. Moreover, the early developments of VC imaging algorithms tend to use receiver ghosts of primaries instead of primaries themselves, because they provide a better illumination of the subsurface. So the multiple attenuation methods developed for VSP data must be reappraised for VC data. Now, let's talk about vertical acquisition cables inland. The acquisition style of vertical cables lends itself to overcoming many of the problems associated with surface land seismics. The very nature of land seismics implies the ability to use a 3-component source and record multi-component data. By coupling the cable onto the walls of fluid-filled boreholes we gain the opportunity to record 4-component data versus 3-component surface data. In other words, VC can be characterized as a 12-component survey versus a current 9-component surface survey. The added pressure data can aid in the up-down separation. Also, the orientation and coupling of each receiver are guaranteed when positioned on a fixed vertical cable. Here we are showing a surface receiver array in vertical cables. We will show data corresponding to these receiver distributions in the next slide. This figure shows synthetic data corresponding to a horizontal array in vertical cable, as described in the previous slide. The source was in the low velocity zone. The ground roll in the surface data is disturbing primary events in the surface seismic data, whereas the ground roll in the vertical cable is limited to shallow receivers in the low velocity region. In other words, we can see that the vertical cable data in this figure have more or less the same appearance as VSP data. There are strong downgoing events and weaker upgoing events. Also, the PS converted waves are more important in VC data due to the larger incident angles than those achieved in the surface seismics. But more importantly, we notice that the data quality compared to that of the surface data is significantly improved. High amplitude ground roll is limited to the receivers, which are located within the low velocity zone. The high amplitudes can be attributed to the large impedance contrast at the surface and base of the low velocity zone, which effectively traps much of the seismic energy. Eliminating ground roll is accomplished by simply removing the near-surface receivers located within the low-velocity layers. Receivers located below the low-velocity zone display data quality similar to that obtained in typical marine streamer surveys. The simulated static effects due to the irregular base of weathering are still present, but they are not as significant compared to the equivalent surface data. By placing the source below the low velocity zone, we see further improvements in the VC data quality. Again, we notice that the ground roll is present only in the receivers located within the low velocity zone. Also, many of the multiple events in the VC data are now much weaker compared to the prior data set. When the source is located beneath the low velocity zone, the base of weathering acts more or less as a free surface with a reflection coefficient of about -0.6, reflecting the majority of the upgoing energy back down. Remember, there is a large selection of iMode education lectures, which can further enhance your knowledge of wave propagation, elasticity, electromagnetism, wave field sampling, wave field decomposition, and imaging. Thank you for listening to this iMode education lecture.